Okay, so this video is on the electromotive force and internal resistance, so topic 5.3. And this question, or questions can come up for this in paper 2 and in paper 3, or actually paper 1 as well. But paper 3, it can be used for graphing, which I'll do on the next page. I have seen that used before in terms of like having to calculate some things from the graph. So when we're talking about EMF, okay, EMF is essentially the potential difference that's been supplied from the battery or from the cell, okay? So the EMF is the amount of work done per unit charge. So going back to that voltage equation, it's work done per unit charge in pushing an electron completely around this circuit. Okay, so that's the electromotive force. Electron, motive, making it move all the way around the source. Now, as we know, let's say it's gained that voltage, that potential difference, sorry, not potential, that EMF here. It then has to go around the source circuit and it deposits it. It doesn't really deposit it, it uses the work as it goes through that resistance. So across here, we know that we get a resistance, so a terminal potential difference of V is equal to IR. So the EMF of our circuit always goes through and it kind of drops it down and it's used across that resistor. So we gain that work done per unit charge to push it round, and the potential difference between this point is how much work is being done to move it across this point. So how much is gained, how much is lost in terms of you thinking of it like that. Although that's a little bit of a model to just kind of work it out. That was a perfect system. Physics is not always that perfect. So sometimes inside the cell or the power pack or the battery that we're using, there might be a little bit of resistance inside there, which means that the electrons are also going to have to work to pass through the cell or the power pack, the component, whatever it is that's powering our circuit. And we call that the internal resistance, okay? And the internal resistance is going to be given by the little symbol of R. Okay, so this internal resistance means that we're going to have to do some work across here. Now, because again, current is going around our circuit, okay, I have my IR across here, so I have some potential difference that's being lost through here. So we call this the lost volts. Okay, so if we had a perfect system, there was no internal resistance, all of E should go to V. Okay, looking at our Kirchhoff's second law, our loop rule, okay, the EMF should loop through so that we have it all being then being used to be worked across to get through that resistor there. But if we have got some internal resistance, we have to consider those lost volts, okay? So in this case, we have to say that V, okay, the voltage that's being lost across up here, is equal to I times R. Remember, our I is going to be the same in a series circuit, okay, using Kirchhoff's first law. There's no junctions for it to split out, so my current is the same everywhere. So if I'm looking at this, I can then come up with an equation for my EMF. So my EMF is equal to my terminal potential difference, we call it terminal potential difference, the one that's being used in the circuit, plus my lost volts. Okay, so in this case, I'm going to use my equation for working out V. So using my V is equal to IR, and for my potential, so my terminal PD, okay, so V terminal, V is equal to I big R. Okay, so the potential difference across my resistor. So in this case, my EMF is equal to IR plus I little r. Now, essentially, that's the same as saying E is equal to V plus IR. Okay, sometimes they like to put this in different ways. They sometimes just like to kind of confuse you a little bit, and they might not give you the resistance, they might give you the voltage instead. So just watch out for what values they have given you. Again, if I look at this, you sometimes do see the equation as well as the I outside of the brackets and then R plus little r. And we can also rearrange this as well to actually have in terms of the terminal potential difference. If I wanted to work out what my resistance is getting, okay, so that's usually what they actually want to find out in the question. They want to know how much potential difference has been deposited across here if we had some internal resistance up here. So in this case, I would look at V, so my terminal PD, how much potential difference is being given to the resistor. That's going to be equal to the EMF minus the lost volts. Okay, so again, just being able to rearrange that equation. So V is equal to EMF minus lost volts. So just being really careful with that. And that's usually what you have to figure out. But if you're having to do a paper 3, then what they might get you to do, this also comes up in paper 1 as well, is that you might have to do this from a graph. So if we're working it out from a graph, we've said that terminal PD is equal to the EMF minus those lost volts. So kind of just rearranging this a little bit to try and linearize my equation to try and get it into that nice form of y is equal to mx plus c. I just did a little bit of tidying up over here. So I just switched these around. So I had V is equal to minus IR, okay, plus E in this case. And then I just pulled it round. So I had V is equal to minus RI plus E. So in this case, what we can then do is start looking at a circuit. So if we were doing a circuit measurement, I might then take some different voltages and current readings. So let's say my power pack, I'm going to turn up my voltage. I'm going to use my circuit. I might put my ammeter in. Let's say I've got my resistor here and I have my voltmeter in parallel. So I'm going to measure the potential difference and I'm going to measure the current. Okay, so I'll get my different readings. Obviously, we try and do trials if we were going to be very reliable with this. And I plot on my graph my current against my terminal potential difference. So in this case, I start thinking what I can work out. So then I look back at my equation that I rearranged for. So V is equal to minus Ri plus E. And this is actually the shape of graph that you get. In this case, what we have is a negative gradient. And that negative gradient, I'm not surprised about because I have negative R in here. So the gradient is actually equal to the internal resistance. Okay, so in this case, we're going down and then we're going across. So we do our change in Y over change in X to give me the value for the internal resistance there. Okay, the plus E is the EMF, which is my y-intercept. So the y-intercept is my EMF, and that should make sense as well. Because when the voltage, when the terminal potential difference here should equal the EMF up there, is when my current should be at zero, because there should be then for no internal resistance through that little resistance in the actual power pack itself. So that does make sense as well. So usually on a question, it might give you a graph like this, and it might say, what's the internal resistance? Or it might say, how do you work out the internal resistance from the graph? You want to say it's the gradient. How do you work out the EMF? It could be, again, a little multiple choice, and it's giving you a few different things. Or it could be on a paper 3 question. But just making sure that you can rearrange that equation. So the EMF, remember, is equal to I R plus R. If I multiply it out through, EMF is equal to V plus IR, so that IR together plus I little r. So that becomes V is equal to EMF minus IR, same as saying minus RI plus E, to be able to get through to that. Okay, so it doesn't actually give you the equation in this form in your data booklet. You have to be able to solve for it. And that's a little bit on EMF and internal resistance.